I also uploaded an example journal assignment that we talked about on the first night. So this hopefully will give you a good idea of what to do with that, and you'll see that it's nothing scary or too onerous, just a description of the journal that the student did. The student that I used did a really good job on this assignment. If I bring up the syllabus too, just to review that. We'll kind of look at where we are. I will not be able to be here next week, but I will record a session. Does anyone have experience with iTunes U with UB, with other classes? It doesn't look like it's too widely used. For another class, I'm having trouble with it. I mean, I successfully recorded a session and posted it, and no one can see it. And I'm not sure why, and it doesn't seem really consistent. I'll go and it looks like it's gone. So what I might do, just if it's easier, to make a YouTube account. And that seems like that'll be easier, and then share that with the class so you can go on YouTube and watch. I'm recording now. It didn't work last week, but this is going to be a challenge. The AV equipment's gone, so I'm going to have to remember to switch slides on this and then on this so that the video recording works. I said I'm not just doing that for next week when I'm gone, but I'll try to do that for every course, so it's an additional study aid for you. You don't remember what I said about something, you can go back and listen. First time I've done that in earnest. I tried it last summer at a summer course, and it worked pretty well, so I'm going to try that the entire semester. Well. As we see here, we reviewed this all yesterday, but the first journal will be due March 3rd. So just kind of looking a month out, we're going to talk about projections and data models and structures generally tonight. We'll have a recorded session for February 10th, a week from tonight. We'll have another class on February 17th, and the first exam is the night of February 24th. Obviously, the content would only be on these 4 classes. Short answer, somewhere between 10 and 20 questions. No multiple choice or that, but they're fill-in essays, but small. Nothing more than a paragraph at most, and some things could be a line or two. There'll be some math, especially with like decimal. There's a good hint. Decimal degrees to lat long is guaranteed to be on there, that we talked about last week. But I'm not that mean. I try to pick numbers that are easy to convert, so you don't necessarily have to use a calculator. If you want to, you can, as long as you use a smartphone, but just obviously don't Google anything. Then after that, we will have 4 more classes. The second exam will be April 7th, covering the second part of the class. And then, as I mentioned, the final day of the class is May 5th. It'll be here before we know it. The final exam will be in class. It's not cumulative, but I may sometimes ask if I want to see people do a little better on a particular question from the first 2 exams, I will re-ask it, but I usually give a heads up on something like that I'm planning on doing that. And we'll cover that. We usually, if there's time, every class before an exam, I'll kind of go over and review with you. And that's a good bonus for those that attend, because there's some good hints in there about what I'll probably ask on the test. I noticed this happens a lot. There's a final exam period class or exam listed for this class. You can ignore that. I'm not planning. I think sometimes they automatically give me a session in the final exam week to reserve, but I'm not going to use that. So I think there is one listed, and you can just ignore that. We'll be on May 5th. We'll be done. But get you out and set you free for the summer. The journals are staggered. The first journal is due a month from tonight, and then you can see where the second one's late March, then early April, late April, and May 5th. We'll spend the last couple classes doing the presentations that I mentioned last week. We'll talk about that more as that gets closer. So tonight is the first full night. How many slides do we have tonight? 37, so it's a long class for the night, so we'll take a break about halfway through every night for you guys and for me. probably more important for me sometimes. And I'll stop the session and record a new session after that. And I'll let you know whether I end up posting things on iTunes or if I just create a YouTube account. The latter is right now seeming like it's going to be a lot easier for me and for you to access. But again, no class tonight, so you can come if you want, but I won't be here. But I will refer you to the YouTube video or whatever, however we do that for your reference. Are there any questions before we get started? I think someone wanted to make a quick announcement. Is that?
Yeah. Hi. I'm just going to do this from back here because I can't get the front room. My name is Max. Some of you guys have seen this presentation a few times, but for those of you that haven't, Alpha Kappa Chi is a coeducational environmental fraternity on campus. We are a professional fraternity. We are not social. We are basically a group of like-minded individuals who just really love the environment and doing environmental things. We do tons of community service. We play a huge role in the campus garden. We're working on different professional projects. We have a few info sessions, and this upcoming weekend we have a few hikes and ice skating. It's free to anyone who wants to attend on our dime. So if anyone's interested, come up to me and I have some flyers. I'll be happy to tell you more about it. Thank you.
Cool. Well, thanks. And as I promised, we talked about map projections and projecting from a globe onto a flat surface last week, and I remember my promise props. We'll start with just kind of a review of what we talked about. A large part of what we talked about last, I have to remember not to stray too far from the microphone, that we talked about last week was the act of map projecting a map. The Earth is round, which everyone hopefully knows. So anytime you want to represent a round surface on a flat map, you are distorting the map. And as we talked about, that comes with a penalty. Any map on a flat surface is distorted. And so one way to really illustrate that is, this is the hardest part. Let's say we were to fly from class to Japan. And I thought I had a string, I forgot it, so that's iPhone cords come in handy for these things, right? So if on this map, if I were to ask you and you use this map, what is the shortest distance from Buffalo to Japan? I'm standing in the way.
Do you want help holding that?
Yeah, would someone mind? Yeah, that would be so much easier. Oh. Someone mind holding it or maybe closer to the mic?
Oh.
This will only take a second. And this is the first I've actually remembered this year. I had a perfect record of forgetting to do this, which has been broken. So look at this. This is Mercator. I think this map is not conform. Oh, it's Winkle triple. It does not preserve direction. So we'll see that if we go from Buffalo to Tokyo. It kind of looks like the shortest distance between 2 points of straight line, right? Go right through Europe, China, and Turkey. Thank you. But if I were to look at the same distance on a globe, I better bring the globe, but my daughter's going to be upset. It's her globe. Just for a good cause. Notice the completely different path. So in essence, in reality, the shortest distance from Buffalo to Tokyo is right over the pole. And indeed, if you go to FlightAware or a website that tracks flights to Asia go right over the North Pole. I've never been in Asia. A friend of mine whose husband went, loved it because he flew over the Arctic and North Pole and saw all the ice. I think that would be really cool. So this is a way to really illustrate how distorted a map on a flat surface is, and review the slides from last week as another when we talked about that. There. Okay. Is there a question? No?
Actually, when you go into Asia and coming back to it from Asia is taking a different road because of the wind that you know. So sometimes you're not taking the closest.
And that's a good point. They don't. There's other factors than just the shortest distance. I always thought before I learned this that it was safer because there's less turbulence, there's less heat. I think that's part of over the pole. so there's less chance of thunderstorms and so on. But the winds are a factor, and they may take a slightly different route going and coming because of that.
And not only that, and part of the North Pole doesn't have the radar stations. You can't really track the airplane.
Oh, I didn't know that. That's
Right
interesting.
there,
That's kind of scary.
somewhere like that.
Yeah, don't tell.
Over there.
Yeah, exactly. It kind of feels like the North Pole, doesn't it? This week. So there's my prop. We'll have another prop maybe today too. So hopefully that's an easy way to remember how, when I teach this to professionals and I say maps are distorted, that people get upset with me. How could they be wrong? And then this is a clear illustration of how that is. And remember the acronym SADD: shape, area, distance, and direction are the 4 ways a flat map can be wrong. And obviously on this projection, direction is wrong by a lot. I mean, if you look at the 2 lines we did, they're not even close. So we'll review. We talked about the act of projecting a map last week. We'll go into a little more detail tonight about specific projections that you'll see a lot. And a common projection is the world Mercator. This is a familiar. Doesn't that look? I told you I would do this. This is going to be a challenge. You'll see. Now that doesn't appear on the projector very well, but this is a map of the world that this projection you may see regularly. It is a familiar projection. It's cylindrical. We talked about the different types of projections last week, so that means there's heavy distortion at the poles. It makes countries near the poles look way larger than they are, and it minimizes countries and continents near the equator. So it becomes a cultural and social issue as well. We look at this. Antarctica looks bigger than like the whole rest of the world combined on the Mercator projection, and that's not accurate. It's kind of like that here too. This projection's not as bad. I mean, Antarctica still looks pretty big, but it's not. I mean, it's not small, but the cylindrical projections really distort the features at the poles. So I talked about last week how specific projections are used for specific areas. I mean, we'll talk about state plane and UTM as very localized projections in just a slide or two. But here's a very common projection that's used for mapping the United States. And again, if you're used to seeing maps of the United States on a wall map, it looks right, doesn't it? It looks like a typical map of the United States you might see, and that's a USA Albers equal area, it's a conical projection. The US isn't necessarily near the pole or the equator, so a conical projection works well. And equal area in the name of the projection means that the areas on this map are accurate. Direction isn't, shapes may be distorted, and distance. If we were to measure a distance from New York to LA on this map, it would be off. But the areas are correct, so the A and the acronym. In other words, if this map, the relative size of Texas on this map to Nebraska is correct. If Texas is, and I don't know if this is true or not, if Texas is exactly 2 times or the size of Nebraska in the real world, in this projection, the area that is depicting Nebraska on the map would be half the size of the area depicting Texas. Does that make sense? Because area is preserved. Where obviously in other projections the area is not preserved. When you look at Antarctica, and it's way bigger than it looks a bit bigger than it is. Does that make sense? So Albers equal area is a common projection. But often we're mapping in a small area. You're mapping for a project on one site or from one city. When you do a GPS assignment that the lab TAs will assist you with, you'll be mapping around UB. So in many of those cases, we need a localized projection. And going back to my example of the orange peel, where we have a algorithm, it can be set up so at that one point in space, the map, even though it's flat, is very accurate, and the distortion becomes worse as you move away from that space. So a lot of different projections have been developed for specific areas. So within that area, even though it's a flat map, all four measurements are very accurate. It's only when you move away from that area when the map becomes distorted. So a very common projection, we use this all the time, is called Universal Transverse Mercator, or you'll see it abbreviated UTM. I think I use a UTM projection every day of my career. It's not something that is unusual. It's a rectangular coordinate system of the world. In case there's interest, I won't ask this, but Gerardus Mercator invented it in the 16th century. And units are measured in meters. We talked about last week how the advantage of a flat map is a consistent scale of measurement, inch, foot, and so on. UTM's measurements are in meters. And it splits the world into 60 zones. So if you think about the circumference of the Earth, there are 360 degrees, right? If you go all the way around the equator, you've traversed 360 degrees of a circle because you've covered the entire circumference of a circle. So if there's 60 zones, each one of those 60 zones will have 6 degrees of longitude. I'll open up Google Earth too to talk about this. And I'm more interested in the first bullet here than the second. So beginning at the 180th meridian, the international date line, the opposite of Greenwich, England, we start with zone 1. And this map shows, I'm not going to worry about the horizontal lines here, the vertical lines show that zone, that particular UTM zone. I'll bring up something on the web too, because that's kind of hard to read. So here, if you're mapping UTM in the middle of the Pacific here, you would use UTM zone 1 as your projection. So Universal Transverse Mercator is actually 60 UTM or projections. And the one that you pick, we are right, this causes problems. We're right on the border of zone 17 and zone 18. So sometimes in Western New York, I'll see data mapped and projected to UTM zone 17. Sometimes I'll see it projected to UTM zone 18. And I'll just bring up maybe an easier. And here's a map showing the UTM zones just in the United States. So even though we're technically in zone 17, data sets created by New York State often are in zone 18 because most of New York State falls within zone 18, if you see that on the map. Does that make sense? So these are 60 different Universal Transverse Mercator projections, and the one that's most ideal will be the number that your longitude falls within. Does that make sense? And again, this is very widely used. It's worldwide, so that's another advantage of it. We just did a project in Texas and we use UTM zone 14. And did a project in Morocco and use UTM zone 29. I mean, it's something that's universal, just like the name implies. And so some additional details about the projection. With a UTM projection, we have a thing called a central meridian. That's given an easting of 500,000 meters. We talked about eastings and northings last week. And the equator is given a northing of 0. So this line is the equator. And this is the central meridian. So right in the middle of zone 17, you'll kind of, that maybe like around Cleveland or so, there's a central meridian. And that has an easting or an X value of 500,000. So if we followed zone 17, it's going to be hard to visualize on this, but we'll try. If we follow zone 17 down, so there's the central meridian through Cleveland, down to the equator. It ends up off the coast of Ecuador here. That point in the UTM zone 17 projection has an X value of 500,000 and a Y value of 0. An easting of 500,000, a northing of 0. So the Y or the northing would go up as we travel north from the equator. So here's an example. This is a good point to bring up Google Earth. I have it switched. Oh. Well, they do that now. They actually also display for you the zones right in Google Earth. If you go on Google Earth, Tools, Options, Universal Transverse Mercator. Normally you would get the degrees, minutes, and seconds down here. That might be hard to see. That's what you're usually used to seeing on Google Earth. But you can go to Universal Transverse Mercator. Move it. And get the zones, and I can hover over to find a specific location. And we see here, zone 17. The easting is roughly 680,000 meters. So we're 180,000 meters east of that central meridian that goes through Ohio. And the northing for campus is roughly 4.7 million meters. So we're 4.7 million meters north of the equator. Boy, does it feel it tonight. And that makes sense. 4.7 million meters is 4,700 kilometers. Or 2,500 miles. So if you do the math, that makes sense. So Google Earth not only tells us the distance laterally from the central meridian and the distance from the equator, but it gives us the zone we're in, zone 17. Any question that makes sense? Another common projection that is used for even a smaller area than UTM, that also I think I use on a daily basis for years. These are things that are very important in GIS mapping. Is in the United States, these are called state plane zones, and there's 120. If you look here, there's a map of the U.S. with states. The purplish red lines are where states have been further divided into specific zones. So these are actually for local small projects. This is preferred even over UTM. So for mapping, say, mapping features out in the parking lot, like you'll do later. State plane, Western New York State Plane is the name of this one. Would be the preferred projection. There's a Central New York State Plane, so that in Eastern New York, and a Long Island State Plane that covers the island and the city. Depending on the shape of the state, and I think this is somewhat arbitrary, some states are divided horizontally, some states are divided vertically. California has 6. Montana, oddly, just has 1. New York State, again, has the 4. So this Western New York State Plane is a map projection that was invented specifically for people that want to do accurate mapping in Western New York State. Many other countries have similar specific projections for their respective countries. So the United States, being a pretty large country, needs quite a few projections to get this level of accuracy. It said there's 120 if you set them and count them. They follow state and county lines. I think probably on the end drive in the lab, the ESRI data sets that come with the software, there's a polygon shape file. We'll know more about that, what that means as the course goes on, defining these specifically. There's just another. Each, I don't want to get it. For databases, each state plane zone has a specific code. I don't want to worry about that. There's a map just specifically zoomed into the northeastern U.S., giving us the suggested projections to use within each county. The Buffalo and Rochester basically are, state plane west. You go east of there till Utica is central and so on. As I mentioned, other states like Ohio are split into northern Ohio state plane and southern, rather than east and west. Any questions about state plane? And if you work on GIS projects in this area, you'll use Western New York state plane as the map projection a lot. Some more descriptions of these state plane zones. Each zone has its own projection system. I always forget this. It's not a big deal because obviously I'm not going to ask something like that, but it actually uses the UTM projection behind the scenes for states that are north-south and a Lambert conic projection than a east-west. That's not, more for information, it's not really a big deal. The central meridian is 2 million feet instead of 500,000 meters. And at the southwestern corner of the projection is the origin point of 0, 0. So down in the southwest corner of Western New York State plane example is where you get 0, 0. These are kind of specific things that I wouldn't try to trip up anyone on the test. I'd ask more big picture questions about projections, but it's good information to have. Some common rules of thumb about projections. These are important. Try to use a projected system as much as possible for any analysis. And this will, as you start to do labs, you'll see what I'm talking about more. You don't use data that's not projected, that's stored in decimal degrees. As we talked about last week, a degree is not always a degree. See how the longitude lines converge? And we looked at this last week. We have a 15 degrees longitude at the equator is this big, but it gets smaller and smaller. And if you think about it, at the North Pole, if we're just a couple feet from the North Pole, 15 degrees of longitude is like this big instead of 500 miles. So what good is a mapping unit that changes? Like say a meter over here on this side of the classroom is different than the meter on that side of the classroom. A meter wouldn't be very useful for you then, would it? The advantage, again, of a projected coordinate system is anywhere you map, units are consistent. Whether you're at the North Pole or equator, an inch is an inch. A foot is a foot. I've also seen, because of that, I've seen analysis get weird. It's a common mistake to do clips. And we do a lot of area analysis. Being an environmental company, someone will say, this is the footprint of our potential project. How many acres of wetland does this project affect? If someone tries to do that analysis using decimal degrees, sometimes we get weird results. Data that you're analyzing should be projected into state plane, a UTM, or something like that for accurate results. It also makes more sense to tell someone, there's 50 acres of wetland versus, or 35 miles of this pipeline cross wetland versus 1.26 decimal degrees. And no one's going to know what that means. In the lab, we'll talk about how to convert between projections, remotely sensed imagery, and DEMs, which don't worry too much about that specifically. We'll cover DEMs in about a month. Use UTM. Data sets that cover a larger area tend to use UTM. If you download data from the New York State GIS Clearinghouse, they'll make a note to cover that for those of you looking for data for assignments and labs in a couple of weeks. The New York State GIS Data Clearinghouse provides data in UTM. I just had to download some data from the Pennsylvania GIS Clearinghouse, and that's in UTM Zone 18. Because that data set is too big for a state plane zone. But smaller areas with a smaller footprint use state plane. If you were to go down to Buffalo, Erie County office and get a copy of the property boundaries in Erie County, it would come in state plane. It's a smaller area, and within one county, you can clearly define a correct state plane zone. Whereas if you look here, I mean, if you wanted a data set of all of New York State, which of the four are you going to choose? That's a tough choice. So in that case, they use UTM. So both, as I mentioned, both UTM and state plane are widely used, but state plane tends to be better with a smaller footprint or smaller extent. Does that make sense? Those are the type of questions I would ask versus, how many meters is the false easting or something like that. A big picture that's frankly going to be more useful to you than memorizing things. Projection makes a difference. Here are three, centered on Meads Ranch, Kansas, here, the pink circle, which we'll talk about in a second. Here's three different projections of the United States overlaying each other, and obviously they look notice how they look very different. So especially, this is a bigger deal as you're mapping a wider area, but the projection that you choose can make your map look wildly different. And we already saw that a little bit with my example here with the flat map. So it is something to consider, especially if you're mapping a larger area. We had quite a conundrum. We were mapping from scratch a potential natural gas pipeline in the west that went from Montana to the Pacific Ocean. And we created our own project, which I don't recommend. Created our own projection because it crossed three UTM zones going east-west. So which one do you use? They were concerned about accuracy, so they made their own that was centered on that pipeline. We don't have to do that I can only think of a couple times in 12 years we've had to do that. But that is an option. We'll make sure the TAs hopefully don't make you do that in the lab. If they do, tell me, I'll talk to them about it. And I'm not sure I could teach it, 'cause I'm not sure how I would do that myself. I'd have to stop and think. Okay, any questions about projections? We're talking about another element of mapping. So switching gears a little bit, but not completely, we'll talk about datums. And a projection is used in conjunction with a datum. We saw how a projection is basically a mathematical formula from going from this to this. But specifically, this globe here is perfectly round. They make them perfectly round. The Earth is not perfectly round. The Earth is, because of the effect of spinning, the Earth is fatter at the equator than from the poles because of the effect of gravity. And obviously, though minor, there's deviations on the surface of the Earth that aren't reflected here. You have oceans in some areas, and you have mountain ranges in others, with the Alps, Himalayas, Rockies, etc. So a datum is a known and constant surface which is used to describe the location of points on the Earth. They define the size and shape of the Earth and provide an origin point, as I've written here, for coordinate systems to map. And they work with something called an ellipsoid, which is the actual formula that approximates the true shape of the Earth, which is not a perfect sphere. And just like projections are defined for specific areas, we have datums that have been defined for specific larger regions of the globe. So in this example, these shapes are very distorted, for effect. I mean, frankly, if you flew out into space and looked at the globe, it would look like a perfect sphere. These are minor, I think to an astronaut's eye, they're minor deviations, but they're important when it comes to mapping, even though you may not see them. So the Earth really doesn't look this weird, but it's good for effect. So here, think of the black outline indeed as the shape of the Earth, and then we've developed an ellipsoid or a mathematical formula approximating the shape of the Earth. In this case, this datum and ellipsoid is optimized for North America. whereas this is a different geoid or datum that would be used in Europe. That makes sense? So datums are also developed for specific areas of the Earth. And again, rather than a projection which takes a globe and puts it on the surface, on a flat surface, a datum helps us more accurately define the actual true shape of the Earth. And here's another, any questions? So here, and again, this is widely distorted. So a datum that you'll see a lot, the last slide showed about specific datums designed for different continents, but there is a generalized datum that can be used anywhere in the world called WGS84 for World Geodetic Survey. It was developed in 1984. That's where the 84 comes from. So often GPS units will use that datum. You'll see this datum used a lot, here and overseas. So WGS84 is the best known example of a global datum. It works anywhere in the world. It is the best example. Frankly, I can't think of another one other than that. That's how widely used it is for me. I'm sure there are. Whereas local datums best fit local areas of interest. And we'll have that on the next slide. Questions? So again, it's important to know that I'm more interested in projections for practical use, but this is important to note as well. These are some local datums that you'll see. This one less and less often. The North American datum of 1927 was developed, not surprisingly, in 1927, and it was defined by the Clark spheroid. So the datum has behind it, like we saw in the previous slide, an approximation of the surface of the Earth. The Clark spheroid, let's go back, is this, and that point is Meads Ranch, Kansas. I don't know, someone probably could tell you, I can't, how they arrived at that. And if you're, I'm surprised I haven't done that, some kind of a geography nerd, but you can actually go to that point and there's a cool little monument you can look at in Meads Ranch, Kansas. So the Clark spheroid, which was defined in 1866, defined this shape of the Earth, and the datum touches the spheroid, like we saw on the other slide, in Kansas. But that was, and again, that was in 1927. If you think about what's happened, well, a lot's happened since 1927. The satellites, air traffic, and so many things were developed after 1927. And with the advent of satellite data, they discovered that the datum was inaccurate. The approximation of not only the datum, but the approximation of the shape of the Earth that was approximated in 1866 was inaccurate. So with new satellite information, satellites measuring the Earth's surface from space, the spheroid was updated to what's called the GIS 1980 ellipsoid in 1980, which is a more accurate representation of the true shape of the planet. And based on that, they updated a new datum called the North American datum 3 years later in 1983. And this is still widely used. I thought someone said that there's another datum coming out. Someone told me that. I don't know if that's true. That would be, like, earth, no pun intended, earth-shattering to geographers. Yeah.
NOAA is doing a sounding data.
Okay, that's why I've heard about that. I haven't seen any results, or have you?
They haven't finished it yet.
Okay, so
They're
that,
still scanning.
yep, that'll be big. That's a pretty big deal when that happens. I mean, look, there's only 2 of them since 1927, so that's going to be, all our maps will have to change. I don't want to be there that day. But we're still using this, and that should say NAD 83. You'll often see it abbreviated to NAD 83. And they gave up Kansas, and now it's referencing the center of the Earth with NAD 83. So a projection, or I'll get to that in a second. So this reviews, in my experience, and probably most, if you're in North America, I mean, obviously there's people that aren't. These are the datums that I see most often for my North American experience, 99% of the time or more. The North American data, 1983. When I first started GIS 20 years ago, you saw a lot more NAD 1927 in use. If you went down to that property records office that I talked about in Buffalo and got the Erie County property maps, they were referenced using 1927, even in the 1990s when I first started using that data. But around 2005 or so, the official maps have been updated to NAD 1983, and I haven't seen a 27 datum in a while. It's mostly these two. And then worldwide, even though we're mapping in North America, you often see the WGS 84 datum used as well. In Morocco, we used a datum called Mershish. Morocco, they speak French, which I'd never used before. I think specific to North Africa. So that was kind of cool. Is anyone that has experience with this, other parts of the world, used any other datums? No, that's okay. That's no problem.
Niagara Falls datum, you'll still see the International Great Lakes datum
Oh, yeah,
from 55.
interesting. Yeah, that's a vertical datum, or is that horizontal?
No, there's a horizontal and vertical.
Okay, I've seen vertical reference to the mouth of the St. Lawrence. You'll see that on official maps sometimes in the Great Lakes. Reference to the sea level at Rimouski, where the St. Lawrence empties into the Atlantic. Interesting. The proper datum is just as important as projection. So when you So if we talk about examples, a projection uses a datum. So it's not just Western New York State Plain. Western New York State Plain is the act of going from this to this for Western New York, but instead of going from a round globe, you go from the datum. So the projection will actually say Western New York State Plain NAD 1983 datum or 1927 datum. Same with UTM zone. So two examples. The projection also needs to have defined what datum, what spherical object did you start from? Yes.
I'm confused. You had mentioned a difference between a horizontal and a vertical datum.
Okay, yeah, these are used for mapping horizontal surfaces, a location on the Earth's surface.
Okay.
A vertical datum, I don't think I covered that, but it's worth at least mentioning. Vertical datums are used to estimate height, means like above sea level. Where everything I've talked about, it's actually an excellent question. Everything I talked about is horizontal in the fact that it helps us find a location on Earth, on the horizontal plane. Where a vertical datum helps you estimate how many feet above sea level that spot is. Does that answer the question? Mm-hmm. And NAVD 1988, I don't know as much. We don't have to deal with that as much. Our clients, at least as well as many, are often more interested.
NAVD 94 would be
94. Okay, yeah. Most people are interested more in the horizontal. Where is it, than the sea level. But it's worth mentioning. Any questions? We're now going to talk about vector data models, because we're going to switch gears a little bit from projections. I'm not sure why it says review this. I'll draw my graph here again. So we're talking about on a flat surface. We looked at how a location on Earth is represented with two coordinates when you have a projected coordinate system. So this location at UV is represented, with this easting and this northing, 600,000 meters, 4.7 millimeters. This is no different really than what you did in math class when you would plot things on graph paper. So if a coordinate is 3, 4, that's the location. So this is what's called a vector data model. That makes sense? Can you see how this applies more generically to something like this, where you have an x, y direction, an x direction laterally, and a y direction vertically? The same thing here that you did in math that we're doing on this projected surface. Most GIS data is using this vector data model. And what that means is we are mapping discrete objects. And discrete objects can have 0 to 2 dimensions. We talk a little about the, yes?
The easting and northing coordinates, is that from, what did that have to do, with the zones, or is that just from
It has,
where you start, where's your point of origin when you're where those numbers fall?
the point of origin is, and yes, the easting and northing do have to do with zones here, but more generically, it's another word for x and y.
Right, but where are you starting?
The origin is the 0 point in UTM. This will differ for every projection. Is the equator.
Oh, this year.
So we're 4.7 million meters north of the equator. The origin on the easting, or the x, is 500,000 meters west of that central meridian for the zone. So in this case, it does apply to the zone. But other non-UTM projections also have an easting and northing. Does that help clarify a little bit? So this is 680,000 meters east of the origin. And the central meridian of a projection, I might still have that up.
So the x is from the zone,
Yeah.
and then the y is from the equator.
The equator, yes.
Okay, I got it.
So, and that's an excellent question, because what you'll see, if you map it in the wrong zone, often the y will be similar or the same.
But I'm sorry, it's not like the end of the zone, you said it was the middle, right?
Yeah, the middle zone is 500,000.
Right,
So we're 180,000 meters east of that, which goes through, I think it's a little west of Cleveland, if you look at this. So if I mapped, I wish Google would let me do that. I don't think it does. If I had ArcMap on here, I could show you. I don't see. If I mapped Western Europe using zone 18 instead of zone 17, the y would be about the same, because we're still the same distance from the equator, but the x would be about 500,000 meters different, because now the origin is, in fact, it might even be negative. Now the 500,000 point in that zone is different. It's over here near Albany. So we would be less than 500,000. We'd be 500,000 minus however meters it is from here to Albany. So it might be like 200,000. Does that, I hope, it can be confusing here because it's actually 60 different projections. Hopefully that helps clarify how that works specifically with UTM. But more generically, easting is just a term. I've even seen it used for state plane. Easting is the x number, and northing is the y number, in a more generic definition. Is that?
So would the line between 17 and 18, if you're using 18, be 0? Or like, why does it start at 500,000 in the middle rather than like, where's your starting point if you're in that projection?
That's somewhat arbitrary when they define the projection. I don't know if that comes out to 0 or not. It depends on, I think that would differ based on your latitude.
Okay.
Because if you think about it, the horizontal distance is greater down here. That's a good question. Any other questions on that? We'll make sure before we move on. So the vector model is taking these eastings and northings, x, y's, and mapping a feature as a discrete object, a geometric object, like in math class. So a zero-dimensional object is just a point. One point in space, 3, 4. Google is showing 1 point in space if I were to add a marker. Let's see. No, it doesn't like that. It didn't do anything. So I've added a point in Google representing, sort of where we are. And there, that point is represented with those coordinates in UTM in this particular example. So it represents one discrete spot on the globe. And those coordinates, I think I mentioned this last week, describe exactly one spot and only one spot. Otherwise, it wouldn't make sense to use that. So zone 17, 680,000, 4.7 million describes that Fillmore building on UB and only that. There's no other place on Earth. So in other words, what you look at when you get a set of coordinates, you can pinpoint exactly where that is. There's no ambiguity. And the point is 0 dimensions. It doesn't have a length. It doesn't have an area. So we tend to use that for small features. I'll bring up Google Maps that aren't linear or areas. Sometimes this is an example. So if we look at one of my favorite things, restaurants. As it's mapped here, I see multiple vector point features now on the map. These all represent restaurants. They represent one discrete location. That is, if I go back to the slide, a zero-dimensional vector object. A one-dimensional vector object is a fancy way of saying a line. So if we have 2 points, and we connect the dots, that is a line. And a line is defined as a set of points. It can be more than one. I mean, this is the simplest type of line. It's just a from and to. But I could have 3 different coordinates, 3 different vertices. Vertices are points that define the line. So it's 3 points, and you connect the dots. That's a one-dimensional vector feature. Does that make sense? So it's another way of mapping discrete objects. Let's look at Google. I think we can pick out some lines. So the obvious example here would be the roads that they show. The 990, various roads around here are drawn as linear features. Lines are one-dimensional. They have a length. I can measure the length of the line. It doesn't have an area. So it's one-dimensional. Now I'm getting too hungry. Two-dimensional vector object. I should really eat more if I come here if we're going to talk about restaurants. A two-dimensional object you might refer to as an area or a polygon. We GIS people like to call them polygons, but area works. It's a self-connecting line is a fancy way to say that. In other words, it's a line whose start point is the same as the end point. The line closes in on itself and creates an area, an interior area. So this has 2 dimensions. We can measure a length, you can measure a perimeter, and you can measure the area of this polygon. That's a 2-dimensional object. Does that make sense? And if we look at, I can see multiple polygon vector features on the map, and I'll see the area representing UB is a polygon, because UB is a vector feature. No, it's quite described it. A lot of words for it. There's now another one representing. It has an area. You could say, you know, UB is X number of acres or whatever the size of it is. We also see Lake LaSalle, other various lakes as polygons. You know, the part of the Audubon complex there, the park next to UB is a polygon. So can you see this is certain to be a question? I ask this every time. Just in case of missing slides, there's a few more slides in there I want to add in there. I will certainly ask, there's no question that I'll ask this, for you to give an example of a point, something that can be represented by a point, something by a line, and something by a polygon. I mean, think about that now, think of how you might answer that. They are, these are geometry. Think you did this in math class. For me, it was many years ago, and for you, it wasn't so many years ago. You graphed, you got coordinates, maybe in a math final exam. I think it was 7th or 8th grade when I did it a long time ago. And you got coordinates, and you on graph paper kind of drew out lines and areas. So you've done this before. It's geometry, it's vector based. And this is best used for discrete objects. That's the slide that I have to dig up, because there should be the slide after this about what I'm about to talk about. The vector data model, and this is probably 90% of the data you'll use in lab and in real world, are the vector data model. So you'll use this. I'll focus on this more than other things in the class, because I believe that's what you'll use more than other things. Vector data model, if you think about it, is a good way to represent a discrete object. And a discrete object is something that has a clear start and stop. So if we think about our Google Maps, I mean, the road has you can clearly define where the Youngman is. It's not ambiguous. You could clearly define the location of a restaurant or a hydrant. I'm giving away examples for the test. But something that has a clear definition, or the boundary of UB is something that you're either on UB or you're not. The desk is a clear, if I were to map the room, I would use a vector data model. And here, this is part of the desk, that's not. We're not going to get into an argument over where the desk stops, because it's pretty clear. Continuous data is a different type of data, where the boundary is ambiguous. And I'll use, since it's fresh and I'll use climate. So it's awful out. I mean, unless you like winter. I mean, the weather here is horrible. I don't know why I live here. And so, let's say, if I had money, I'd say, I'll help you all out. Let's all go to Miami and do the second part of the lecture from Miami. I haven't looked at the weather today, but I bet it's pretty nice there. As we're walking, we need exercise. As we're walking from here to Miami, are we in this bitter, horrible weather? Then this is awful. And then all of a sudden I step here, it's beautiful. Just look, back in winter. It's a gradual transition. It's a continuous climate, temperature, things like that is a continuous data set. Do you see the difference between that and something like a desk that has a clear stop point? The climate, the weather will gradually improve as you go south from here. And if I asked you each to map where you think the weather got better, each one of you would draw a different line. But if I asked each of you to draw the desk, everyone's going to say it ends here. Does that help? It help a little bit with continuous versus discrete data. That's a good question usually too. And vector data model is best used to map discrete data that has a clear start and stop. And a third, I think there actually might be a lab on a three-dimensional object. We don't get into this much. We talked about point is 0 dimensions, line is 1, area is 2. ArcGIS has the capability of a 3D shape. Or in this case, and I can't quite draw this as well, you've got X and Y, and then you have Z, which is a third dimension, it's height. So X, it would be width, X is this way, Y is that way, Z is the third dimension. We've got a cube here to describe that. So the way that we map that is X, Y, and then Z. You can actually, now I'm getting, this isn't as metaphysical as it sounds, you can map 4D. In the fourth dimension isn't some weird thing, it's time. So there's a thing called time analyst in ArcGIS where you can actually measure not only the cube's location, but where it was at a particular point in time. Because obviously that it may move. But we'll leave that for now. Any questions? Okay, that's well. We'll talk a little bit more, and then in a little bit we'll take our break. Things are moving well, probably because of the slides. Just one or two. This other data model that I'm talking about, we learned about vector data model in the last couple slides. The other major data model, which we actually will talk quite a bit about, is the raster data model. Or you'll see it, a common term for this is a grid. A raster data model is represented with a consistent set of squares. It's completely different than the vectors we looked at. So we have a grid with a defined size, width and height of squares, and that square has one value. If you think about this, raster is a good way to measure continuous data. In each one of these elevation, and we'll have, I'm not going to get into this too much because we'll have entire lectures about the raster model. Either at the end of the exam 1 period or just to start for exam 2. I don't remember offhand. So in this case, this raster, the value is a color. So a photograph is a raster. The image background here on Google Earth, this is never going to show up on this projector. I'll try. Is a raster. And so you know how your digital camera, well, people don't even, or your phone, no one uses digital cameras anymore. That came and went. Has a resolution. You may be familiar with that. This picture I got is 96 dots per inch. That means basically that it's a raster, and these cells in 1 inch on the photo, there's 96 of these. And each of those 96 squares in that inch that your camera or phone took, it has a color. And you put that all together, it's like a photo mosaic with those puzzles. It makes a picture. And so that's why a higher resolution photo is more accurate. Because if you set your phone to 300 dpi, now there's 300 squares where there used to be 96 in the same spot. So the photo is much more accurate. Because now those variations in color over space in the photo, there's a lot more room for that. And that's why if you've ever done that, you'll also notice the file size of your photo is a lot bigger because it takes a lot more memory to store all those extra squares. If we think about, let's say we were mapping this room in a raster data model, if the square was 20 feet by 20 feet, I'm only going to fit a couple squares. And if they were doing color, so this whole area of the room, I can only store one value. However far 20 feet goes from the wall, maybe it's a here or so. But if I were to map the room using 6-inch squares, if you think about it, I could represent this room much more accurately. Because now I could give the color for this 6 inches. Oh, it's different. If I'm going to report a color in my map here and here, I can report 2 different colors. But if I'm using a 20-foot square, I'm going to come up with some average color for this whole 20 feet. It's not going to be as accurate. But it's going to take less memory. try to imagine 20-foot squares, maybe there's 5 or 6 in the whole room. If I were to put out layout 6-inch squares, is going to be hundreds or thousands. So the trade-off with the raster data model is the accuracy versus the size that you need. If I went to like a 1/10 of an inch square, I'm going to have millions of squares to represent this room, and it would be overkill. Maybe I don't really need that level of detail. So there's a law of diminishing returns at some point, where the extra file size that you get from these tiny squares doesn't really give you benefit. Does that make sense? So when people map raster data sets, they make that decision. You know, at what point do I get the optimum amount resolution or accuracy without overloading my file size? So I'm usually getting to. If you zoom in, it's never gonna. It looks much clearer on here. You can only barely see this on this projector, is not very good, but the photo background on Google Earth is actually just a collection of squares with colors. Maybe at the shore. Yeah, maybe we'll. Then I might go to sleep. Do you like that better for the whole class, or you'd rather have them on that's awfully dark? What do you think?
Can we leave like one light on so we can still take
I don't know. Yeah, that might not be feasible.
Yeah, there's generally a way to put the lights off there next to the overhead projector thing, and then have the rest on.
Maybe I'll play with that during the break. Because it's hard to see that, but then if it's too dark, we're all gonna. I wonder if I can turn these on.
There we go.
Excellent. Nice compromise. So now, we still might not see it. Now it does this thing where it kind of goes flattens out. It's not going to let me get in close enough to see the squares. Oh well. I never used to do that with the tilting. You can sort of see it there, where each of these is a square. There's slightly different colors to represent the different things going on in this farmer's field. And that's actually called remote sensing. And there's a whole class on that the department offers. It's awesome. And we'll talk a little bit about remote sensing later. But I won't do it justice. Dr. Bian's remote sensing, you'd spend a whole semester talking about that. They didn't have that when I was here, and I wish they did, because it's something I find really interesting and never had the chance to really delve into it myself in depth, other than to use what someone else does for me someday. Any questions? And just to review, so again, the raster data, we'll talk a lot about these cells and their uses later in the course. Continuous data. Hopefully we see the difference there. 2 review slides here. Just to reiterate once more, geographic coordinate systems, measurements are based on a sphere, latitude and longitude. Projected systems, flat surface. Measurements are with a consistent unit, foot, meter, and so on. I think that's getting close to 8. Let's take a short break now. Start back up in 5 or 10 minutes.